All right, go ahead and answer. The correct answer here is C. So this mass, this rock, it's just telling us that it's moving in a circle, and the circle itself is horizontal. So it could be like the conical pendulum from the last section. It could technically be a mass on a table. The string is tied to the rock, but we would, well, it doesn't matter if there's friction or not in terms of the question, because it's just asking us about the work done by tension. In either case, the tension force is why we have a centripetal acceleration. The centripetal acceleration would be towards the center of the circle, the circular path that the rock is twirling in. In the case of this first case, like the conical pendulum, the tension has x and y components, and it would only be the x component causing the circular motion. The y component would be balancing out with gravity because it tells us the circle it's moving through is a horizontal plane. In the second example, the tension itself is what's causing the centripetal acceleration. The answer to this question, though, is C, regardless of the situation, whether we have situation 1 or 2. The reason why goes back to the dot product. So the tension, if we just assume it's constant, which it would be in the horizontal situation, I suppose, we can write the dot product as the force dotted with displacement, or we can write it generically as the force times the delta S times the cosine of theta. Or we can write it as these x components multiplied together. Ultimately, let's look at this F delta S cosine theta. So the work done by tension, the force we care about is T, this tension. Delta S is at any instant the direction the rock is traveling in. So for example, let's take case 2. Let me draw as if we were looking down from above. So here's our rock. We know the tension is pointing in towards the center, but the delta S, let's say the rock is twirling counterclockwise, at any given instant, the delta S is tangent to the circle. So if I'm talking this next moment, tension still points towards the center, but delta S is tangent to the circle. I could continue drawing this all the way around. Tension will always point towards the center. Delta S will be tangent to the circle. That means the angle between these two at any point in time is 90 degrees. Ultimately, what I care about is this theta. If theta is 90 degrees, cosine of 90 degrees is 0. The work done by tension, regardless of what the tension force is, the work done by tension will be 0. And that's because the force is perpendicular to the displacement. So going back to what we mean by taking the dot product is we're multiplying components of the force that are parallel to the displacement. Well, the tension does not have a component parallel to the displacement. And this cosine theta term is what shows us that in the equation. But we can always go ahead and just remember this. We don't have to memorize it. The equation will allow us to reason it out. But ultimately, the force itself, if it is perpendicular to the displacement, the work done by that force is zero. If you remember just talking about centripetal acceleration, the tension was responsible for making the rock go in a circle. It was not responsible for making the rock speed up or slow down. Speeding up or slow down, we had to have a tangential acceleration. So we needed some sort of force that was tangent to the circle. So this is just another way of looking at this motion in a similar way.